Uh, Today we're going to see the concept of block diagrams and bond graphs as is related to a mechanical spring C element. So what I would suggest we do is we're going to have the block diagram here on the left hand side, and then we'll have the bond graph models on the right hand side. Just make a little lining here to make it pretty. All right. What is the law that controls how this element behaves? Do you remember? Isn't it true that we say that F is equal to some stiffness times the displacement, right? Do you remember how this is called? Right? This is how this element behaves. This in nature. This is what it does. We know that this spring here stores potential energy. And we can safely write this equation like this. We can write that this is F is equal to K is the stiffness, yeah? But in this kind of elements, we can also write it in terms of the compliance, which is the inverse of the stiffness. The same equation could be written as 1 over C times the integral of x dot dt, right? This is another way of writing this equation. Okay? So these two forms, this one and this one. So this is the stiffness form, this is the compliance form, but they mean the same thing. Okay? So what I would do, because most people are comfortable with this form, I'll just use that one to say that in this stiffness form that F is equal to K times the integral of x dot dt. Yeah? Very good. This obviously is an integral form, so let's just write it here. Also, what does it imply? It implies that if x is the input here, if the output is going to be f, or if the velocity is specified, the output is going to be f. So why don't we write it down in here? This is my output. And this is my input on this side. Yeah? And we could also say that, given this input, you get this output. You could say, we can use other words. You could say this is the action, and this is the reaction. You could say this is also the cause, and this is the effect. Huh? You can use all these terms. The idea is that you have a variable that comes in and one that comes out. So isn't it true that if we represent this as a block diagram, we will have that in here you have the input as x dot, and then you have x dot, you perform an integration here, and 1 over s, let's say, and you have x over here, and you multiply it by k, and out comes f. Let me use the Simulink notation so that we are consistent with our drawings here. The Simulink notation calls for this not to be a square but rather a triangular shape again here, this kind of element. Let's just do that. Very good. So this is the representation of the integral form of this spring, or we call it C element for compliant element, yeah? So this is the integral form of the equation. So what I'm trying to say is here, the input is this one, the output is over here. Always, if this is in a computer statement, always executes from right to left, right? This is the result, this is what you're giving. Or this is the action, this is the reaction, or this is the cause, and this is the effect. This idea of cause and effect leads us to a concept that has a new technical word called causality. Who was responsible to cause the action? In this case, we gave it the velocity and we caused the force, right? So this equation corresponds to this block diagram, and this corresponds to the integral form of this element. Okay? But, you know, we could write the equation a little different. And here, we'll say, okay, why don't we draw a line in here just to separate things? And we say, you could say, we could write, we could write it in this form. In this case, I am going to say, what about if x is the output? You know, let's say that you, in here, you take the derivative of both of this. So we differentiate both sides and we say this is df dt is equal to k times the integral of this is, you know, we differentiate, this is going to be x. So I can write that x is 1 over k times the df dt. Yeah? And I am going to do a little frame to both of those forms. This one right here is obviously the integral form, and this one right here is the derivative form. So this is the way we write it in derivative form. Let's see, did we do something wrong here? I think we might have. Okay, hold on for a second. This is fine, 1 over k times df dt. No, I think we're fine. No, did we? No. See here, this is the, if you take the derivative, you have this is the, this is the velocity on this side, right? Because, yeah, so if you take the derivative of both sides, it's actually x dot, that is the result right here. I knew I was missing just a little detail in there. So this is the derivative form. We also know that that if you have dx dt is equal to x dot, right? Consequently, you can say that dx dt is equal to 1 over k times df dt. Yeah? And so this form in reality is the derivative form of this. See? These two equations are the same. Yeah? So this is the derivative form. How do we represent this in block diagram form? This is saying that the input that comes in here is f, yeah? Then this gets differentiated dt, so you have df dt, derivative of the force, and then multiply this by 1 over k, and out of this comes x dot. See? Compare this one, it's totally the reverse. Here x dot is the input in this. I'm just going to change colors just to illustrate that. This is your input here. And this is your output here. Look at this one. It's the reverse. This is in and this is out. But you see the point here is that depending on which way the input is and which is the output, we either get it in the integral form or we get it in the derivative form. Let me just make a small correction here, just again for consistency. Draw the little triangle in there. Like this is going to be like this. Yeah? Okay. So the block, what can we conclude about the representation of the equations in block diagram? I mean, what is the? Let me ask the question correctly. What does it depend on the way we draw the block diagram? What controls it? What controls our block diagram? The equation. That's the answer to that question. So the conclusion that we reach is that block diagrams are really a graphical representation of equations. Okay? Why don't let's just write that down, because I think it would be nice if you have that in your notes as well. I'm just going to put it in here. I say, okay, block diagrams you say are graphical representations of equations. Keep that in mind for the rest of all these lessons, but that is the way it is. Block diagrams are the representation of equations. We can have this kind of block of the equation, and we have this block diagram. We have this equation, and we have this block diagram. So this is the integral form, and this is the derivative form. Yeah? So I think that it is quite important to to make that conclusion, you know, because from now on we always will relate block diagrams as the graphical representation of equations. Any questions about this? Let's see. In here, now we switch our attention to the same element in here. The element that has been assigned to represent this spring is a C element. C stands for compliance element, okay? And the way bond graph models work is they have an element and they have a symbol that looks like this, okay? This symbol has a horizontal line, or if it is, it could be also vertical line if it is position 90 degrees. And then it has a crossbar like this. What this means is that this one right here is the input to the element. This is the output of the element. Okay? So just imagine yourself if you were to hold this line. Let me put your little fingers here just to make a little more dramatic. There you are. There's your hand, and it's really holding this. Just imagine yourself. You feel it, squish that line like that. You feel it, squish. Now push it to the left, following this piston that is over here. In other words, you need this piston to push, right? You need something. You don't want to just stop the line, but you want this crossbar to push it. So isn't it true that when you do that, hold it and then push it to the right, imaginary, you know, this is like parabola that I am saying. So push to the right, you make an effort, right? You make an effort to push to the right. So we're going to call this out variable, we're also going to call it effort. Yeah? And this variable that comes in, we're going to call it flow, the one that is on the other side of this little piston. Okay? What this means is that this output variable, this is your F variable. And the input variable in here, this is your X dot. So this representation that you have in here says that F is equal to 1 over C in this case times the integral of X dot dt. See? This symbol, as you see it here, corresponds to this form of the equation. But you could see it very clearly now that in here, these two are equivalent, see? These are equivalent. So, whenever you have this equation and the symbol, is exactly this and therefore this. So this symbol as it is in here represents this block diagram. Remember what I was saying a moment ago about the languages? We are talking about the same equations, but we are expressing them in just a little different representation. These block diagrams are understood by Simulink. Yeah? But these bond graphs are understood by CAMG. CAMG stands for Computer Aided Modeling Program with Graphical Interface. Right? So in here, when we have it in this way, we have the equations that say what you just you have seen in here, and that you know that dx dt is equal to x dot here. These are the two equations that conform the integral form of the C element. And in this case, if we go down and we represent now the C element in a different way, watch this. We're going to put the C element here, like this time. But now we're going to reverse the symbol. We're going to have it like this. Okay? So, let's work this together. If you, let's say you have your little hand there again. There you go. You're gonna push it with this crossbar. You know, you cannot push it with a line. You don't have no way to push. So this one, hold it with your right hand, squish that line, squish hard, and now you push it towards the C, to the left. So this one becomes the input now, and this becomes the output. But the input here is really the variable, the force F, yeah, and the output is x dot. Okay? What this means is that this symbol represents the derivative form of the differential equation, because it is all we put it in from here, Take the derivative of both sides in there so that we can find this form. You have that, take it says df dt. Df dt is equal to 1 over c times x dot, yeah? Or you can write this, the way you write it is that x dot is equal to c times df dt, right? See? If you have, keep this in mind, that dx dt, which is x dot, this is x dot, then it follows that dx dt is equal to c times df dt. And this form that I just wrote, this thing here, corresponds to this picture. But think about what we are doing here, see? This form is completely equivalent. If you replace c by 1 over k, you got the same equation. See, I'll just put it in here like this. And when we use bond graph notations, we usually use the c variable. We use the block diagram, you can use k, but c is 1 over k, it's the very same thing. Should I write it down in here? Just in case, eh? So, since c is 1 over k, then it follows that dx dt is equal to 1 over k times df dt. Yeah? So, we have a complete equivalence between this integral form, the way it looks here, this C element in here, to this equation, to this block diagram, or we have this form of the C element in the bond graph notation that is completely equivalent to this derivative form in the block diagram, and I have shown you also that the equations are exactly the same. So, conclusion of this: we have an integral form and a derivative form. And you can express the integral form in a block diagram notation like this, or you can express it in this symbol like that. Simulink will understand it this way, CAMG will understand it this way. All right? And so if you have then the equation this other way, this is the derivative form. You have the representation of that derivative form over here. This would be equivalent to this form. Does it help what I'm in this sort of a parabolic way of speaking? If you hold it here, look where the instrument to push is. You push it this way, right? In other words, it comes out of C, right? Pushing it to the right comes out of C. In this one, you're going to push it towards this thing, with this thing. Here you push it to the left, it comes into C. Always this crossbar is the effort variable, and this one is the flow variable. So when you see a symbol like this, you relate either to this block diagram or this equation. When you see a symbol like this, you relate to this block diagram or this equation, which is totally equivalent. So I have demonstrated for you the complete equivalency between the two methods while keeping two different graphical representations.